All right. Awesome. Thanks, Russell. I'll include a link to your slides as well as the GitHub link that Nick posted in the chat.
Great, thank you.
Of course. So first up for the AGU poster presentations, we have Luz talking about Komodo model access in geospace. Pretty sure I had seen, yeah, Luz is on. Luz,
yeah, I'm
sorry.
here. So yeah, let me see how this sharing thing works here. Share screen, share window, click on the window. Okay, we should be seeing a green background poster. Hopefully.
Yep.
Comes up. Okay, so you see that. And yeah, so Komodo, we have a bunch of us at the Community Coordinated Modeling Center have been developing Komodo, started by Asha Pembroke, to use a functional approach in Python to get access to simulation models like MHD models or other models in heliophysics or in space physics, and be able to do that in a consistent way between the different models so that users in the Python universe can use numerical models and their outputs. And so my presentation at the AGU was focusing on how I used existing Fortran and C source software to connect to Python and integrate it into the Python Komodo universe. And I have three things that I'm mentioning here, and among others. So one example was how to read a model output that used encoding or like a compression algorithm within the model to make the model outputs as small as possible. But that, of course, requires a large library of Fortran code. And what I did is just developing a very simple interface function and then F2Py instructions to say which parameters are inputs and which are outputs. And this is just showing that this function calls an internal function that's part of the Fortran library, and the instructions for F2Py then result in a function that can be used in Komodo to access the data in the model. And so we have developed this and been able to convert the model using Python into netcdf files that are then much easier to read by subsequent Python and Komodo calls. And so this part is not part of the core Komodo readers, but it's like a utility function to prepare the data to make them more accessible. And that way, if the model has written it into this kind of obscure format, we convert it into netcdf, which is then used as a more standard data format. The other major accomplishment during the last year was to also use a library that I have been using at the CCNC for years in online visualization to make use of the octree log adaptive grid in the BATS-RS model, which is part of the solar wind modeling framework SWMF. And here's an example plot from a publication that describes the algorithms by Gabor Toth. And so a grid cell, a block of cells is defined on a grid and can be refined as you need more resolution in localized spaces. For example, around the Earth, you can have very fine grid cells, but further away, you have very coarse cells. And each block is refined by dividing each direction by a factor of 2 to make smaller children blocks. And then you can go further in those child blocks until you have reached your final resolution that you want to have. And the software that I'm have been integrating into Komodo actually does a search through this tree structure from coarsest to finest resolution levels. And when you put in a position inside this grid, it'll quickly go through this tree and then finds the block that you are inside of, and then you can do trilinear interpolation within the final block to get your interpolated value of the magnetohydrodynamic code. And it is possible to define like C structures. Here, for example, I have this octree block structure and enable Python to allocate arrays of those structures and then subsequently use that C program to use the grid structure. And we have compared that, like originally there's a Python package that reads the model. I don't know how much time I have. I'm going way out of time here, I think. And so
You have a couple more minutes.
Yeah, and so I should come to a conclusion here. And then the third part of the poster presentation essentially describes how we can use other packages such as a field line tracer that in turn will use the advanced interpolation scheme. And so yes, Komodo has an initial value solver that uses just the functional approach. So you define your functions of magnetic fields, vectors, for example, and then the initial value solver can then go through the function and create a representation of the magnetic field in terms that looks like field line traces. But we are still working on optimizing this. This process is very slow even if you use the advanced interpolation. So we have to maybe resort to a more direct tracing of individual field lines. So that's something we are still working on. And here's like a field line tracer interface that traces the field line in both directions with the magnetic field and against the field. And then you get magnetic footpoints on the Earth and the trajectories through space, like shown here. And so that's active development. But all those features uses also C program, and it's more efficient than using Python interpreted available functions. And in the middle here, there's a few things that we have been working on that Komodo makes more straightforward. So in the IDL CCNC visualization, we had 3 coordinate systems or dimensionless units, SI units, or custom units for each model that are defined. But Komodo can now do that on a more general basis. So you can actually specify what unit you want for example, in plasma density or electric field. And if they're not listed here, the program that we're using, like SymPy, can automatically apply any other conversion factor. So if we want to go into Gaussian system, for example, we can do that, and that's more flexible than the previous IDL code that we had at the CCNC. And I think I should stop here to give others the chance.
Thanks, Lutz. Anyone have a super quick question? Oh, I see Bob raised your hand.
Hi, Lutz. Is this available in the master or these features? Or is it a branch or something? I didn't see it documented in the master, but
in the master, it's those features, the readers and tracers are part of like the model readers, and we are still working on getting those model readers into a separate package and putting those documentations into the GitHub documentation.
Okay.
So it's something that's still in work.
Yeah.
And so we have the OpenTTCM reader, SWMF, Betzeras reader. It's all part of the reader package, and they'll be transferred into the NASA GitHub package very soon. And I have to work on making the documentation so it's.
Yeah, I understand. It always lags a little bit or a lot bit in my case.
Yes. And I certainly have to
the,
learn about this myself, like how to do that.
Oh, I know.
So Darren has done some of that, and Darren and I will work on that.
Do you have comparisons in terms of the speed with respect to Komodo? Or I'm sorry, a Chameleon? Do you have that down there?
Chameleon, no, haven't done that much. We have done a little bit comparison between the CCMC online visualization and Komodo, and we are seeing that we're getting similar numbers in terms of reading data and accessing data. We have not done that with Chameleon. Chameleon uses the CDF, and yes, we have to do that. But we've seen that Komodo reads NetCDF files very quickly, and
okay, cool.
Thank you. Comparable.
Yeah, it's a great development. Thanks.
So Darren will talk about the plotting tool that comes out of those readers. Okay, thank you for your question. And I should stop sharing if I need to do that, or somebody else stop sharing. Okay.
Awesome. Thank you so much. Well, with that, let's go ahead and have Darren. Are you online? I don't actually see Darren. All right. Well, Rebecca, you had asked about going and talking also about Komodo. Would you like to go now?
Sure.
Awesome. You have about 10-ish minutes.
10 minutes. That's a lot of time. Hold on. Share screen.
Okay, cool. Oh.
All right. So I'm assuming you can hear me. Can you see the correct screen with the poster?
Yes.
Yep.
All right, cool. Let's go. Okay, hi. Welcome back from the holidays and such things. So we have a trio of Komodo posters. You just saw Luce's. There, I can post a link to Darren's in the chat so that people can look at that. Darren's focuses on the visualization, not only the defaults available with Komodo, but the specialized ones that are custom designed to show satellite. What word did I want to use? Custom designed to show some things that I'm going to show here, just to keep it simple. Let me not get ahead of myself. So the motivation for Komodo to begin with is that it's really hard to access all of these different versions of model data. I'm going to click on here. Keep forgetting this is not my touchscreen computer. Don't touch the screen. Okay, so we have CCMC is the official repository of all of the space weather models. Not to say that some of them aren't hosted other places. Sorry, such as SWIPC and our colleagues across the ocean in Europe and Asia and so on. But we host a lot of heliophysics models at CCMC, and all of them have their different flavors of output data, which makes any comparison between models and observational data quite challenging for users in heliophysics. So the motivation for designing Komodo in the first place is to levelize that playing field, as in provide one easy way to access the model data for all of the models that we host. And preferably in a way that's easily extensible, so it doesn't take us 10 years to do this, right? Okay, so what you see here is a list of models hosted at CCMC. Now, this isn't all of the models. That would be really complex diagram. It's complex enough here. The colors show your different areas of physics in heliophysics. The dashed red boxes are models that we're currently working on adding to this Komodo interface. And the ones in red boxes are models that we currently have. Now remember, not all of the models are listed here, so there are some models currently accessible through Komodo that are not on this diagram, and some models that are currently in progress that are not on this diagram. Okay, that's the motivation. There's some links in this poster to different Komodo-related repositories that are important, and some other CCMC resources here that we showed at AGM. So first of all, what is Komodo? I think most people here know what it is, so I'll go quickly here. But here's a good example here of what it can do. That didn't come out as big as I was hoping. Okay, so basically with Komodo, with a few lines of code, you can functionalize any data set. The picture here is showing even an example of how to functionalize one particular time series data set, in this case, total electron content. And there's a aspect to Komodo where you can get the LaTeX representation, and with one simple command here, you can have an interactive plot using the default plotting features of Komodo. The way Komodo is currently designed is it depends on Plotly. So if you're familiar with Plotly and the nightmare of code that goes behind it, you'll greatly appreciate just that one line of code and the easy access to an interactive thing. If you want more details on visualization, that's going to be in Darren's poster. So I will skim over that for now. But the point here is that it's with a couple lines of code, basically assigning the proper interpolator to your data set. You can have not only access to a LaTeX representation of your data, easy unit conversion, and the interactive visualization that you can save as interactive, not just as a screenshot. But you can also access these other layers that we've been working on. Okay. Clicking on the wrong thing. So this work builds upon the model readers that Lutz and I have been collaborating on. So I work on the Python side, and Lutz works on the other side, whether it be C, C++, or Fortran. And those will overlap the more that Lutz teaches me. Okay. All right, here's an example of how the model reader layer in Komodo works with model data on the Python side. So it's just an input of this file prefix, which basically tells the program where the data is stored. You can easily access all of the data available in typically for 24 hours for any particular model data that's compatible with that we've written a reader for. So you get the LaTeX representation and all of the features that I've shown before for all of the model data. Okay, including the interactive plot. So this is an example of an interactive two-dimensional plot. In this case, it's a time versus longitude plot. And this is at a slice in latitude and slice in radius. So for this particular model data, it's in spherical coordinates, that it's also capable of doing so in Cartesian coordinates. And you get the full interactivity that's typical of Komodo here. Okay, and notice it's one line. You basically tell it, give it the Komodo object, give it the name of the variable you want, the type of the plot, the range, and the range of your 2 dimensions that you want, and your slice values, and you get this really nice interactive plot where you can zoom, you get the values on hover in the proper color scale, and so on. Okay. On top of that model reader layer is we've been developing some interesting capabilities, such as the satellite fly-through. So this is similar to what's available in PySat, and we're working on collaborating with them also to incorporate that into both. Not only accessible through PySat, but also accessible through Komodo for all these different overlapping areas. So yeah, interoperability, right? Okay, so the goal with the satellite fly-through is to have a fly-through available for any particular model data that we have a model reader for, and have the command be simple. Okay, so here's an example of one of the features. So this is the myFlight function of the satellite fly-through. The myFlight is basically where you give it the trajectory, and then it uses that trajectory to fly, quote unquote, a given satellite through the model data at that trajectory. Other than that, you have to tell it the file name, what type of file it is, whether it's CSV or CDF, not CDF4, etc., what model it is, where the data is, and what variable. And then all of these are just strings where you're telling it what you want, where you want it to put the data in, etc. So none of these are complex things that you have to figure out. Other variations of this function other functions available through the satellite fly-through include where you just get a sample trajectory and fly through the data. You can use a real satellite trajectory and fly through the data. And it's even accessible from the command line. So you can even run this from C or from Fortran, as is used in something else I'm going to talk about in a minute. So simple command input. It's really fast. So this particular trajectory took about 10 seconds to execute completely, which includes building and saving the HTML versions of the visualizations. That means it's still interactive when it's saved. You can output in CSV, as I show here. You can output in .cdf4 or ASCII file, tab separated. And here's an example of the visualization that Darren developed. Hold on, 6-year-old visitor. Here's an example of the visualization that Darren developed. There's 2 versions that are automatically output each time, given that you give it the file name. And it's output as an HTML version. Consult Darren's poster for the links to the interactive version saved online. But this is 4-dimensional visualization. Time is ignored, but in this particular one I'm showing, but there is a version of the visualization where you can actually step through either slices of the orbit or slices in time, as in hours or days and so on. And these are the time series for each of the options here, whether it's Cartesian, whether it's spherical, and then always the actual variable data on top. And you can do this in a variety of coordinates. In fact, all the coordinates supported by SpacePy are available through here because we depend on SpacePy for that currently. The last functionality I'm going to talk through quickly is something we've just finished testing. It's called the Mission Constellation Reconstruction Tool. And it was developed for the GDC Science and Technology Definition Team. So GDC is the Geospace Dynamics Constellation. And what it does is it's built on top of the satellite fly-through and basically executes the same fly-through functionality, but for every satellite in the constellation. And then you can do this for various satellite tracks, as you would expect, but also any 4-dimensional construction of your satellite constellation, whether they're separated by time, latitude, longitude, X, Y, Z, whatever combination you want, as long as it's in the same coordinate system. You can make comparisons, say, between 3 satellites with a particular longitude spacing compared to model output as shown here. You can make a decision based on whatever your science question is. How does what my satellite is projected to see compare with what the model output says it will see? You can also do this comparing number of satellites. Say we have 1 satellite here and 3 equidistant satellites here. How does my resolution improve? How does my error when comparing to the model improves? What error do I need? How many satellites do I need to answer my science question? Those are the motivations for this particular function. And all of this is available in the NASA repo that I already posted in the chat. We are working on expanding our functionalities to other model data, other models hosted at CCMC. We're working on building documentation to guide others through that process so they can add their own models. And note that this doesn't only work for heliophysics, it works for any data, whether it's model data or satellite data or whatnot. So one really interesting application is building this on top of the satellite data available through PySat. And we're working on that PySat and Komodo link. So we're excited to be putting out documentation for this. We have 3 papers coming. 1 paper already submitted to Josh for the base Komodo paper, 3 more coming in the ISPAT Coast Bar Space Weather Roadmap. and more documentation coming for user support. So we're happy to collaborate and have fun with everyone on this. That's it.
Awesome. Thanks, Rebecca. Does anyone have any questions? We have time. If not, we can go ahead and move along. Let's see. I don't see Carl on. Who would be the next poster? Sandy, I believe. Ah, yes, I see you online.
Okay, woohoo.
You're up.
Alrighty, I will keep this brisk and go right to screen share. So going in with the readers theme here, I'll be talking about mostly the happy interface and then a little bit on the SuperMag and time Goofy data that we released from it. Happy, for those that aren't familiar, is an interface that does time series. I've done a lot of work on different time series mission, and often feel like time series are the neglected redheaded stepchild. So many people look at images, but time series are super useful. The happy interface itself, it's a specification and therefore a protocol, but it's also tool sets and client server programs. The idea of happy is to serve time series data. The user should not have to understand the underlying file format, where the file breaks are. They should just be able to suggest a time period and which data items that they are interested in, and then receive that as a file or a stream. And then we should provide tools so that the users don't have to understand it. It's available right now from 3/4 of a dozen missions, and we have an equal number that are soon coming on board. And again, it's a standard specification and tools for doing time series data. Important thing is, Happy at its core is an API, not a tool. Anyone that writes a Happy Aware client, it will work with any of the Happy servers that are out there. Likewise, if you run a server, you can write to the Happy spec, and then you don't have to worry about the client programs. Client programs already exist. As mentioned, it simplifies user queries. The default format is the data description is in JSON, and the data itself is a comma-separated variable. It unifies data from the user point of view, so they don't have to understand file breaks, and they can go across files and even across missions. And it definitely saves bandwidth for servers because you select only the data items you want. You're not downloading an entire FITS or HDF file. You're only getting the data items that you specifically need at that time. For my poster specifically, and the poster is at the bottom of every slide if you want to check it out, I made readers for the SuperMag and Goofy data sets so that they can serve happy streams. And then I don't have to worry about what the users are accessing it with. It simply enables the data.
Yes.
Did someone say they can't hear? Got interrupted by noise there. Hopefully this is chugging along.
All I see is a green slice. I don't see your poster.
Wow, okay. That is very weird. I'm glad you raised that. Let me
You might
stop
just-
there and start
Yeah, you
sharing
might
it.
just try resharing.
Is that visible?
Yes, thank you.
Yep.
Woohoo. Okay. So there's again the poster link, and I've gone through the happy spec, so we're good with that. You can look at the poster for all the detailed wordage, but I just gave you the high point of what the happy spec is. Getting to the core of the poster again, we made some happy readers for SuperMag and Goofy, both of which use NetCDF formats, and realized, hey, now anyone that has NetCDF, these are fairly genericized readers. It's very easy if you have NetCDF files to be able to stick a happy server in parallel to your existing server. So we're not saying replace your existing server, we're saying add a capability very easy, or contact us to add a capability very easy. So pros and cons of having an API or a happy type server. It makes it really easy to combine mission sets. Users don't have to know, oh, this site is using FIS, this one's using NetCDF, and this one's using HDF. Instead, they can just say, hey, I want to grab some stuff from SuperMag and from CEDAWeb and cross-compare, or I want some SuperMag ground data and I want to combine it with some atmospheric magnetic field data and see if there's a correlation. So it removes that burden of file formats. It separates the reader layer from the server or the client layer. And one large advantage is the less that the user needs to know about the specifics of the data format, the data files, etc., the more it helps new early career and out of the field users who aren't already doing this research, but really could use the data set. Obviously, the cons with any easy access to data, it can lead to overconfidence where someone doesn't know the nuances of the data set and they run the risk of overanalyzing or not fully understanding the data set, somewhat mitigated by the fact that most data providers provide a good data description. And frankly, overconfidence and overanalysis will happen anywhere. I've seen people with the X-ray Timing Explorer way back when try to do sub-second analysis on data that was binned in 8-second bins. So, still something to be aware of. Scientists, still a lot of them, especially traditional, trad style science versus people that are looking at Jupyter Notebooks, Cloud, and Python. A lot of the traditional ones like to hug their data. They don't want to stream their data or share it. They want to have the files sitting locally and share and pass around files. And then obviously, if you want to implement a happy server, that's going to require staff hours to implement the reader, which we're trying to mitigate by making as many file readers and as many file formats and languages as we can. So those are the pros and cons of happy. And we pretty much hit all of them with SuperMag. In particular, the not knowing the nuances of the data set, the SuperMag API was underdefined for me, not being familiar with SuperMag, and required a learning curve just to be able to make sure that I was writing good test cases. So all of these are things that one should be cognizant of when doing any kind of reader software. So COSPAR has said happy should be the common data access API for space science and space weather data. Time series are great for science. They're also great for AI because if you're looking for prediction, you're going to be going to time series. And again, it makes it easy. So this is the autoplot tool, which if you're not familiar with, you just look up autoplot and check it out. Autoplot will take just about any data or service and try to make a coherent plot for you. So it took 13 clicks to combine SuperMag and Groovy, so two completely different missions serving happy data. And I just picked a random September 6, 2018 CME and said, hey, let's look at the SuperMag magnetic indices versus Groovy's atmospheric disk intensities. And there I have the data. So kind of nice being able to do stuff in 13 clicks and just a couple minutes to get the data. So it does have a lot of utility, again, for people that want to do data exploration and start adding data sets to what their existing research already is. And then here's another example of the time series data plus Spectra, which is also time series data and therefore happy allowable, that allows you to combine things. So for this specific group, the questions and issues to bring up is really one question. Can you or are you willing to talk about adding happy capabilities to your existing tools? There's Python libraries already that are available through the standard pip install of Happy Client and Happy Plot. There's examples at happyserver.org that go through it. We also have clients and servers in Node.js and JavaScript, R, MATLAB, IDL, Java, BDAS, etc. And so to close it off, if you need to email me, I'm Sandy Antunes at jhuapl.edu. We have the Python libraries, the website's at happyserver.org, and we're starting for new users happy monthly meeting. Our first kickoff is going to be first Tuesday of each month, so Tuesday, February 1st at 9 a.m. EST. Sorry for you West Coasters, but we're trying to be internationally friendly. And that's how we're trying to advance this COSTAR approved server standard. So I'll open things up for questions at this point.
Any questions for Sandy?
I have one.
Perfect.
So I know there have been a lot of packages working together on trying to answer a science question, and that's one thing that Sean presented on at AGU. And I know one problem that we had was, and Sean can speak more on this if he's online, but one problem we had was trying to get this autoplot to work from a Python notebook online. And it took him and a friend, I don't want to name the wrong person. It took him and a friend some, I guess, tech magic from my perspective to get it to work. So is happy plot depending on autoplot?
No,
Like-
completely separate packages. Autoplot just is one of the stronger Happy Aware clients out there. So it was very easy for me to put things together. But Happy is completely separate, as is the Happy client and Happy plot. And there's examples on the Happy server website for quickly getting a plot out using that as your native environment. But that's a very salient point. Yeah, autoplot and Happy are separate. They just happen to share some people. Jeremy, who made autoplot, is also on the Happy specification team.
Okay, thanks.
Awesome. Thanks for that question. Let's see. I think I saw Darren hopped online. Darren, would you like to present your AGU poster now?
I can do that. I apologize so much for missing. I had an in-person meeting that I had to go to that took longer than I expected.
No
Then when I got
problem at
back,
all.
my computer crashed when I got back. So yeah,
Oh no.
I'm kind of scrambling to catch up here with what happened. I was wondering whether he had skipped me or somebody else had filled in, but I can happily share my poster here.
Oh, sure. No problem at all. Go ahead.
Let me get going there.
So Darren, Lutz and I have already gone, and we did reference yours. So we're
Okay.
expecting that.
Okay, so there is some background information that, yeah, I don't need to repeat. Okay. All right, can you see my my poster there?
Yes.
Okay. So yeah, so if Komodo has been talked about a little bit. So Komodo development team has been doing a lot of work and a lot of new things recently. And one of the things that I've been focusing on as a specialized task of this is working with the visualization. And what can we do to enable some of the new visualization stuff to be automatically available, and some of the extra special things we can do in visualization, how to tie that into Komodo and what we're doing. And so part of this poster, again, this is describing, what Komodo is and what we can do with it. But if I jump into the visualization section here, the way this is organized, again, because of the way AGU does their poster, I wanted some eye candy at the top, and then I'll start talking about what it does. But this is just some of the visualizations that can be done from within Komodo. This is showing a global magnetosphere simulation and looking at multiple slice planes, a sphere at the middle, it can spin and rotate, things like that. Data extractions where you're flying a satellite through a simulation and being able to pull that out. And because you're doing that extraction on the fly, in this particular one, I actually also extracted a 100-kilometer box around the satellite to kind of give you some error bars of what's near the satellite to get a feel for what you're seeing. And so these are things that Komodo facilitates. And then just some fancier ways of viewing satellites flying around the Earth and how those look and what you can look at and probe. So Komodo has a lot of built-in visualization stuff into it. So we're using Plotly as one of our primary visualization things. You can use Matplotlib or other things as well. You can tie them in with a little bit of extra effort, but we're integrating tightly with Plotly, and partly because Plotly has a really neat way of making the data interactive and live feeling. So you can zoom and probe and rotate and do all kinds of cool things, as well as the ability to then just export that package into an HTML file that you can easily embed on a web page, and then you can see and do that stuff live as well if you're doing it through a server or some kind of another add-on product. But if you're in Komodo and you're looking at visualization, Komodo will look at what your data is and will automatically generate the appropriate plot file for that automatically. So there's some built-in automatic things. And so if you're sending in, you know, a 1D calling argument and getting back a 1D output shape from that calling argument, it's you know, it's very likely it's a 1D line, and it's going to actually go ahead and then plot that line for you. And so this is a whole long list of possible things. And so here's a really simple example where I made up some data that's just a 1D set of data. That's just some randomization on a sine curve, and it returns a 1D data. And so Plotly is just default komodo.plot, using Plotly to pull this back, and we get this nice image with the plot scales labeled and whatnot. And those can be, if this was a live figure, you would actually be able to move your mouse around, see, it'll tell you what these points are and change values. Similarly, if you do a 2D plot or a 3D plot, it will automatically give you back the right thing, or a 3D plot with lines. But so what we wanted to do is we wanted to provide some augmentation to that. So Komodo will do that and provide that Plotly feature for a wide range of things, but there's some more complicated things that we want to do. And so users have requested some augmentations. And so this is one thing. So we're using an extraction of a satellite trajectory through a CTIP run and getting that data set. And you got, once you have those points, there's actually quite a few different ways that you can display it. The default would just be a 3D line with value on the line. And so the default would be a plot something like this. Well, that might not be the most useful way to display it. And so we've developed this SatPlot 4D little add-on to Komodo that allows you to pull in and display it in multiple ways. And so if you want to just cut out the 3D plot and show it as 1D line plots where you're looking at the values and the positions, you can do it this way and look at the satellite data that way. If you want to instead change it and look at it in lat/lon and say, hey, this is, you know, where the satellite is flying, and you can kind of follow what the satellite trajectory is this way and look at the values as a carpet plot. You can also look at it in a little bit more of a 3D-ish move, this 3D-ish view, where this is a polar view looking down on basically the same thing, looking at how the satellite is flying around. And this is in geo coordinates in this particular one. And again, you can see and probe and look and say, oh, here's that point. Well, here's the XYZ position. Here's the lat/lon altitude as well, and values and times and things like that. And you can do full 3D as well, where this is a full 3D plot around a sphere. And so there's lots of different augmented ways of visualizing how you see those same results. And so those are ways of looking at some of these things. Another thing that we can add to this is we can break up these trajectories and actually have a time slider across the bottom. This one's having to be broken up by orbit. And you can play it as a movie or sweep this back and forth and see how those work. And so a couple of these here, I actually have an external link here that we can go to. And for example, I can pull in this figure. We'll see how fast my internet here is. Not too bad. Halfway there. And so this loads in that same figure, and you can see how, you know, when I move my mouse around, it actually is changing things. And if I rotate and spin, I can actually do different things to dynamically look at the data. And so to be able to actually dynamically see what the data looks like is a very useful thing. And if I load the movie one, this is now playing the movie, and it's actually sliding through across the orbit. And I've broken up the orbit by when it crosses the equator going north on the satellite trajectory. And so it'll just sweep through playing this, and I can pause this, and then I can move it around and continue the movie or whatever and see what I want to see. So these extra ways of viewing and visualizing the results in Komodo are going to be extremely useful. And then again, I give a little more description for what we can do with some of the other satellite output that we do. And so this is a plot where you're actually laying on multiple things and multiple layers. And so we have a number of these models that are available to do some of these visualizations in an online demo that we've got available here. And so you can actually look through For these 5 runs, basically all of the run on request runs at the CCMC. You can generate images using Komodo to do these visualization tools. And so I think I'll leave it at that. There's ways of getting data into Komodo. I'll assume that that's been talked about a little bit and kind of where we're going with this. But visually, what I was trying to get across with this poster and some of the neat new things we can do using Plotly within Komodo to communicate to scientists and display things in a way that they find most useful. So, any questions?
Yeah. Hey, Darren, I got one. So
Yeah.
your demo listed several models there. And then the earlier CCMC presentation, they had, tons more models. How hard is it to get new ones in there? And, what are the conditions for saying, yeah, I'd like to use this to look at my model?
So all of those, the longer list of models is all available in Komodo to do this. We've just chosen a couple of them that we've kind of highlighted then in our web demo. And so it's basically a matter of encapsulating some of the Python commands to execute Komodo into a web page with PHP. And so there's some work there, but whether that's our long-term landing spot for this is not yet clear. So we haven't put a lot of effort into the web demo of being as comprehensive on everything. It's been kind of a sampling of a few things. Komodo itself, the package can do a whole lot more, and we've just chosen some things to put on the web page. But if there are things that people find extremely useful, then we can certainly, with not too much additional effort, create a web front end for it and put it on our demo page as well.
Okay, thanks. Yeah, I might want to have you give more extended demo of this at some point to some of the folks at APL here, if you've got time, maybe.
Yeah, that'd be great.
Okay.
Wonderful. Any other questions for Darren before we go on to our last presentation? If not, Sean, you're up with the PyHC executable paper presentation.
Coolio. Let me make sure that I've got my browser open to the right AGU poster. Looks like I do. Alrighty. First of all, here you can see me, and then hopefully now you can see my screen.
Yep.
Beautiful. All right. So yeah, let's just dive right in here. This poster was talking about developing an executable paper with us. I was proud of this poster because I think this was the first public presentation of any kind that had PyHC's name stamped on it as, we made this. So this was a fun thing to put together. As you're seeing, lots of people on this project. Many of you are on the call today, and we heard from you earlier. So got a good group of people working with me here. I presented on this project before, so I won't go super in depth on what it is we're doing, but just as a refresher. This was the thing that kind of came out of wanting to show off some features of the PyHC packages. We kind of started off with, well, Rebecca had the main idea for the project, really, so she gets the credit there. But we kind of decided what projects we wanted to show off and then worked backwards toward a science question. What we ended up at was we're going to be looking at basically the accuracy of magnetopause models. So you have the magnetopause. I don't know if you can see my mouse. Hopefully you can. And then we're using MMS data. As the MMS satellites cross through the boundary of the magnetopause, we can look at the data and see where that was. And then we can pull in various magnetopause models, take a look at where they were expected to be and compare the two. And our software makes this very easy to do. So an executable paper, again, is like a digital version of a paper where you can run the code that generated, the results, basically, like a Jupyter notebook, but write your whole paper inside of it. I had a good example to one included here that wasn't written by us, just because I think this is the kind of thing to strive for, and I encourage people to click on it if they make it to this poster. Let's see. I actually did stick the executable paper, just a screenshot of it in the poster, which was kind of nifty. You get to see the whole thing right there, or you could click to view it on Deep Note. But, you know, I wasn't expecting anybody to actually read this whole thing. So if you looked at my poster's narration down here at the bottom, I kind of just walk you through like the main bits of the thing. You know, we're using PySpeedas, BasePy, PlasmaPy, PyTplot, and Komodo to do these things. It's a really wonderful suite of packages that lets you get the data, manipulate it, calculate plasma parameters, plot things out, and we've seen now a number of Komodo presentations just this morning, so we know how awesome that is. Sadly, Komodo is one of the things I haven't incorporated yet. That's actually in the future work. My full-time job here at LASP is going to be incorporating Komodo into this notebook starting here in just a few days. So I am getting to that. Something we really wanted to just highlight with this presentation was, you know, we're doing this in a really cross-disciplinary way that, you know, is just kind of heartwarming, and I think a better model of doing science than, you know, the old way of, you know, siloed scripts that stay on scientists' machines, no open science, everyone saying, you know, this is all mine. We're really flipping that around and saying everything's open science. We want to bring in as many people as we can, and this lets us do things that we couldn't do by ourselves, and all sorts of wonderful things. This is still a prototype of an executable paper, so I don't have really a huge deliverable to show you guys, but something that I thought was cool was down here at the bottom. We've already showed one instance where the magnetopause was closer to Earth than the model predicted. And you can kind of, if you take a look at these two plots down here at the bottom, what I'm showing here is there's kind of this crossing right here, right after like this 40 tick mark. And that's where the spacecraft was flying, and this blue line is the model. But if we look at the actual data from the spacecraft, we're seeing, you know, along this vertical line here, some obvious changes in the data that happen between, you know, 30 and 40 rather than after 40, which means the crossing happened earlier, which meant the magnetopause was closer. And we can do this sort of analysis, you know, with, you know, I think it was maybe 20 lines of code in total to get to here, which is, you know, a lot less than other papers around the same kinds of analyses. You know, go us, and go you guys who actually wrote the software packages. I don't think I really need to say anything more about that, so I'll call it good there.
Awesome, thanks, Sean. Anyone have any questions? Comments? Great. Well, thanks again. Looking through the list of people on the call, I think we've made it through all the AGU posters where the participants were able to make it today. So we're going to wrap up earlier than I thought we were going to. Thanks all for coming online and presenting your posters. I'll be, as I mentioned in the notes, sending out links to all of these posters, as well as for the people who couldn't make it today in today's Telecon notes. So yeah, I believe our next Telecon is in 2 weeks. Yes, 2 weeks on the 24th. Topic TBD should be firmed up later today. So thanks everyone, and I hope you have a good day and happy 2022.
Happy New Year.
Bye.
Yeah. Thanks.
Thank you.
Yeah.
Yeah, Russell, are you still online? Ah, there you are.
Still here?
Yeah. Looks like everyone's hopping off. Awesome. Well, if you would like to represent, so sorry I missed that at the beginning of the Telecon.
Not a problem.
But now it'll be Yeah, it'll be here and captured. And if you want to show it to anyone else later, there you go.
All right, great, thank you. Yeah, I'm
Uh-huh.
gonna tweet this out. Let me get my screen going again.
Perfect.
Right.
And I am still free until 10:30. I blocked out this time, so you don't
Okay,
have to
great.
rush if you don't want to.
Wonderful. All right. Thank you for the extra time to make sure to get this on the recording and the
course.
original just to get it on, period. My name is Dr. Russell Stoneback, and I'm presenting today on some new software that I've just released and called orthogonal multipole magnetic basis vectors, or OMMBV for short. So this software has been released on GitHub and PyPy, and it includes some advance in physics that's fundamental for space science. So I really appreciate the opportunity to talk about it. So just a little bit of a background. So the existing vector basis for magnetic fields for mapping electric fields or ion drifts along the geomagnetic field to other locations. The current state has been presented by Landau and Richmond and has been contained within ApexPy, which is also open source software. The unfortunate issue with the mapping contained in that software is that it is non-orthogonal. And by non-orthogonal, what that means is if you pick a particular magnetic direction, in this case, let's use zonal, which is along the magnetic east-west direction. If you have an electric field along that direction and you map it to another location, what you're going to end up with is a combination of zonal and meridional directions for your electric field. So that makes it more difficult to work with this basis, because when things are non-orthogonal, it gets mixed. The software itself only remains orthogonal for a spherical Earth and a purely dipole magnetic field. Now, the actual Earth is not purely spherical, and we have a more complicated field. OMBV adopts the same kind of mathematical backend as the Richmond paper previously, but I've developed a new front end to produce a vector basis that remains orthogonal for non-spherical planets and for more complicated magnetic fields. And the way I'm doing this is I use field line tracing to identify the apex location of a magnetic field, or the highest altitude of that field with respect to the Earth. Now, in this case, for OMMBV, the zonal electric fields and ion drifts remain purely zonal or purely meridional everywhere along the magnetic field when you map them to a different location. So this is much more physically consistent, and it has a number of features that are advantageous for space science. So a big one is that computational models can use this vector basis to remove a dimension from the model. So they can do all the computations just at the magnetic equator, and then after everything is done, they can map those values throughout the magnetosphere to see how things look, but you don't actually have to physically calculate all those things. You can do one calculation ahead of time, and then the mapping is just a couple of multiplications. Similarly, observational data sets can be mapped to the magnetic equator. So currently there's been a few equatorial missions over the years, but each of these satellites is launched at a different inclination and a different altitude. So that means that it makes it difficult to directly compare observations between these missions. But if we map all these observations to the magnetic equator, that removes the dimension and improves the overlap between historical missions. And I will be writing a manuscript right now, and that manuscript demonstrates that any magnetic field that satisfies conservation of flux, which is all of them, has an underlying orthogonal basis. So this is really nice. So OMMBV not only works for the Earth, but I expect it'll work for even more complicated fields like those on Mars or even the Sun. So this is really important for understanding ion neutral electrodynamics, throughout space. And as part of this, OMBV has a built-in check on performance. So I have two ways that I can calculate the same set of vectors. And those two paths will only produce the same numbers if the underlying magnetic field can actually be described with an orthogonal basis, and that I'm getting the correct ones. And I've found, through testing, that the normalized difference between these paths is on the order of 1 × 10⁻⁶. Okay, so there's multiple digits of precision, and OMBV is a valid orthogonal basis. Okay, so some evidence. I have cards here, some plots. So the first 3 of each of these is going to describe the type of magnetic field I am testing with OMMBV. So in this case, this is a dipole magnetic field like any simple bar magnet, and is for the spherical Earth. So in this case, this first one is the apex altitude, how high the apex is above the Earth. And we can see we get a normal kind of dipole distribution. In this case, I've aligned the magnetic dipole with the geographic pole. So all the field lines run north-south. So there should be no change in apex longitude as you move along a field line, and the apex latitude should be near zero. And that's exactly what we find. And in this case, the difference between my two code paths is on the order of 1 × 10⁻⁶, right? So both of the vector paths are very similar to a high degree. If I make it more complicated, I move to a geodetic Earth. You don't see much change in these plots here because nothing's actually changed with the magnetic field. And similarly, nothing has changed with the performance of OMMBV. Now, if I move here to more complicated fields, here I'm going to add a quadrupole term. And this quadrupole is like a pair of dipoles oriented in opposite directions. I've added a pair of quadrupoles to the existing field that we had before, and this is also aligned along the geographic pole. And in this case, now the magnetic equator, geomagnetic equator, is in the southern hemisphere. It's not at the actual, it's not aligned with the geographic equator anymore. And the geomagnetic equator actually varies as a function of altitude. So this is definitely a more complicated field than the previous ones. But in this case, the OMMBV performance remains the same. And similarly, now if instead of a quadrupole along the pole, I add a quadrupole in the equatorial plane, you can see we now get a geomagnetic equator that starts to vary a bit between north and south. But again, the performance of OMMBV remains the same. And again, if I move to an even more complicated field, now this is a normal quadrupole magnetic field in the equatorial plane. So this is a pair of quadrupoles along with the original dipole. And again, the equator here has got like a bit of a Charlie Brown distribution. It goes in the northern and southern hemispheres, but the performance remains the same. And finally, if I actually apply the best representation we have of the Earth's magnetic field, and as presented in the International Geomagnetic Reference Field, or IGRF, if I use that as my magnetic model, the performance of the underlying vectors, again, is about the same as 1 × 10⁻⁶. So these vectors, regardless of the magnetic field, are presenting the same performance. All right, so that's the science output. While developing OMMBV, there's a variety of different techniques that I need to employ to calculate all these things. So I developed a variety of unit test plots so I could understand how each of these components performed as I was developing the software. So to turn those things into art, what I've done is just run them at very high resolution. So this first plot here is the uncertainty in the magnetic apex location and a basis called Earth-centered, Earth-fixed along the Y direction. And in this case, it's how the science outputs vary with the software parameter find step size. So what I do is I run OMMBV from 0 to 360 degrees longitude, and in this case, between -25 and 25 degrees latitude. I run OMMBV at default parameters, and then I vary the find step size parameter. I run it again. I take the difference between those two data sets. I normalize it sometimes, and then I take the log, and then I just plot it. And all the colors here are generated using a perceptually uniform color palette contained within Matplotlib. So I just run this at high resolution, and we can see just modern abstract art pops out, but it's generated from software that's calculating physics parameters and its relationship with the actual Earth's magnetic field. So in a sense, it's the Earth's magnetic field creating this picture. And you can see we really get a broad spectrum of colors that come out with pretty striking patterns. Similarly, I do the same process for this figure over here, but this is the uncertainty of the apex altitude normalized by altitude for the same software parameter. And we can see that this picture comes out where the geomagnetic equator just pops out on its own. So this is not something I specify. This is something that emerges from the software and the science. Similarly, I have a couple images here from the transformations required to support the Earth's actual shape, not just a pure sphere. And in this case, we again get more abstract art. So we can see there's a variety of circles that emerge across all these intersecting lines. This is again 0 to 360 degrees longitude. And we end up with a variety of shading here once we hit 180. And it turns out one of the parameters, one of the transformations in there prefers representing longitude between -180 degrees and +180, whereas the other prefers 0 to 360. So this shading here actually comes out from the loss of precision from a single addition in a periodic space. And this one is a similar thing. I'm just again looking at the uncertainty and the transformations required to support their actual shape. And then the colors again are just coming from a perceptually uniform color map and matplotlib, and the shapes all just emerge from the underlying mathematics, and it produces some pretty interesting pictures. So thank you again for the opportunity to share this work. I started this project about 12 years ago as my first task as a postdoc at the University of Texas at Dallas to help us organize measurements for the ion velocity meter on the CNOS mission. And it's taken me 12 years to get something that's this good, actually back in November. So the science software is open source and freely available for anybody to use, of course. But my work in making the science cards and using OM and BV to produce sciences art is available for purchase as NFTs on these websites. So thank you very much.
Thanks, Russell. I especially like the sciences artwork. That loss in precision made for some cool uncertainty plots.
Yeah, I'm really surprised by how, all the things that are coming out from it. So it's pretty interesting.
For sure.
Well, thank you again for the extra time. So
yeah, of course, no problem. Thank you for staying on to represent.
It's good to have practice, I guess.
Yeah, why not? Why not? Awesome. Well, I will hopefully see you at the next PyHC Telecon.
Yeah,
Have
absolutely.
a good rest of your week.
You too. Cheers.
Bye.